Unit 2, Lesson 3. So as usual, first thing you should do is head to the Science2 Canvas page, and you're looking for tasks to complete for U2L3. You can find that either under assignments or in the weekly calendar on the home page. I'll have a list of everything we're going to do today. Here's Lena. All right, we are all present. All right, as usual, I'll start us with a quick little trip into breakout rooms to share an answer to a little icebreaker question. The question this time around is, you have your own late night talk show. Who do you invite as your first guest? You guys haven't answered this one yet, have you? No, okay. So again, could be a friend, could be a celebrity, could be whatever, doesn't matter to me. I'll give you 20 seconds to think about it and throw you into breakout rooms for a quick share. Was to review homework. The only things you had to do was make sure that you posted to the center of gravity Flipgrid challenge, which was the weird forks on a cup kind of thing. I am currently seeing 11 responses to that. There are 14 people in the class. So if you are unable to get your video onto Flipgrid, just email it to me or let me know if you need help. Even if you couldn't get it to work, it's okay. Just show me that you tried, and you can still answer the question that if you line up the fork and the toothpick right that they hold, the toothpick right on the edge will be the center of gravity for it. So please do that if you haven't done so. I'll share my screen to take a look at the reading statistics. Before I do that though, I guess, were there any questions on the reading reflection for, let's see, it was Hewitt 5.7 through 5.8, which centripetal force and projectiles. Feeling good? All right, let's just take a look at the results real quick. See how you guys did as a class on this quiz. We're set to A. All right. Again, looks like a majority of you got that projectiles slow down at the top of their trajectory. I often think about throwing a ball straight up in the air. It almost comes to a stop before it falls back down. Centripetal force acts towards the center. That is an important concept and something we'll touch on again soon. Any object in motion stays in motion as a projectile, which is kind of a broad definition, but that's the best one we've got for that. Balls batted upwards, what happens to the vertical component? Very good, it slows down as it rises, and then it will speed up again as it falls. Horizontal velocity is not changed, but that's assuming there's no drag, which is not actually realistic. There's always air interacting with it. And then I just thought this video was really cool. Had anyone seen a video like that before? Pouring a drink in like a jet, doing a flip. It kind of was like a popular thing for a little while that someone did it once and then suddenly everyone was doing it. But a demonstration of centripetal force, basically creating false gravity, right? It's you often hear this term artificial gravity. It's not actually gravity. They're just using the force of the spin to keep the liquid inside the glass, which is Velcroed onto the dashboard. It's kind of thing though, it's like if a pilot, you hope it works because otherwise you're gonna be cleaning out that cockpit for, especially he's pouring a Red Bull, that'd be pretty disgusting, I think, very sticky. All right. We'll use some slides to kind of quickly review that too, briefly, before I let you go for an activity. That is the next thing to do. So let me pull up my iPad here really quick, just to reinforce the reading. All right, again, need verbal confirmation. Everyone's seeing a slide in front of them.
Yeah.
Awesome. Okay, let's see how we're feeling. So centripetal force, I know you can see it on the screen there. It acts towards the center. And this, to me, was always kind of surprising. I always thought of centripetal force as being this, right? The motion that was tangential, parallel to the spinning motion. But it's actually acting towards the middle. It's sort of just what's holding it in place. It seems counterintuitive to me, but can be used to simulate gravity, as we saw in that video earlier. And you see this in a lot of sci-fi films. I don't know if anyone's ever seen 2001: A Space Odyssey. They have like this big circular ship that's spinning and it creates this false gravity. If anyone's a fan of The Expanse on Amazon Prime, it's a great sci-fi show they have a spaceship in there too that spins and creates artificial gravity, basically. But just to explain what's going on in this image, it's all about support force, right? That's what you're experiencing under your butt if you're sitting, or under your feet if you're standing right now, right? That's what allows us to feel weight, because we're being pulled down onto a surface. That's the support force. And so you can artificially create this with centripetal force. If you had a sphere that's spinning, here's the direction of spin, then the centripetal force, remember, is acting inwards towards the center. So it's sort of like the ground is being held in place, and this little person here then would be experiencing that, right? The floor is coming up into their feet, and that would create weight, right? And so again, it's not necessarily gravity, but it would be that same person. Our body would probably perceive it as gravity, as being held down to the ground if you got the spin just right. And that downward force there then is just representing that that's where this person's body wants to go away, but they've got that support force underneath their feet. Again, kind of weird, mind-boggling to think about, but that's how centripetal force works. Projectile motion is something we're going to use a little simulation for today. Projectiles always fall in this parabola shape. Even if you were to launch it upwards, you would still get that exact same parabola there. And you can break it down by thinking of vertical and horizontal velocities. And I'm going to keep hammering this home, but that's how we always want to think about this, is what's the velocity going horizontal and what's the velocity going vertical. Gravity, obviously, is what determines a lot of the vertical movement. Gravity accelerates objects pretty quickly. It's technically 9.8 meters per second, but we'll simplify it and just say that they increase by 10 meters per second for every second of fall. Which I know is kind of a weird thing to think, but it just means that after 3 seconds of falling, the object is moving at 30 meters per second, which means that this distance too gets bigger every time, right? For each second of falling, it's going to fall faster until it hits the ground. Horizontal motion for now is just going to be unchanged. Again, we're going to introduce drag in our next lesson, which will alter things a bit. So throwing an object up or down will change the shape of the parabola, and therefore will often change the amount of distance that you're able to cover as well. If you're aiming at a target or something like that, this is something you'll play around with. But again, you always get that parabola shape because you have these two horizontal and vertical forces acting together. And again, looks like most of you felt good about this in the homework, but I encourage you to look at what happens to the vertical, right? As you launch a projectile, this becomes smaller and smaller until it's nothing, and then it increases in a downward direction. Whereas here, again, we're assuming there's no air or anything like that. The horizontal never changes. That arrow is the same value every time. But again, we'll see in our next lesson how that can change. Feeling good? Any questions? All right, let's do some activities to explore this then. First thing you're going to do is a flip grid. It is step number 5 on the tasks to complete list. The title is Water Spin and Bottle Flip Challenge. So if you were into this whole bottle flipping thing that happened like a year ago or 2 years ago, you'll have a chance to revisit it and get into some of the physics behind it. But essentially what you're going to need is a water source, plastic or paper cup. You're going to be throwing this thing around a little bit, so please don't use glass if you have another option. But essentially you're going to fill it up about 3/4 full, and you're going to do a full rotation like that. And if you do it just right, water should not fall out of the cup. And so you're sort of exploring how centripetal force can create this sort of simulated gravity. And you can do it on a smaller scale too. So I'll have you film yourself doing that. There's a question you have to answer afterwards too. Again, always check that. I've been noticing a couple Flipgrid videos where people forget the questions. So again, here's the assignment that you can go to, Water Spin and Bottle Flip Challenge. I've got a demonstration video and all the instructions. The question at the end is, how did none, or at least very little, of the water spill out when the container was upside down during the loop rotation? So you want to talk about how centripetal force pulls towards the middle and creates a support force, right, for the water. That's what the cup is containing, the water, and not letting it spill out. Same instructions on the Flipgrid itself right here, and the same demonstration video is available too. So I'll be here listening if you have questions or if you're not sure what to do. I am going to time for 20 minutes to work on this. The way that you can indicate to me that you're done, so if I see that you've posted your video, is there's this really, really short Edpuzzle that you can then work on. It's 30 seconds long, and it looks into the physics of bottle flipping. So 20 minutes to work on the Flipgrid, and then do the Edpuzzle once that's done. Let me know if you need help. Go for it.
Mr. Hay.
Yep.
Can I leave and come back because it won't record?
Yeah, that's fine. But here's this one. It's called projectile motion, and actually, I wonder if I can reload it. When you open it, it's going to give you a couple options down here. You have intro, vectors, drag, and lab. I want you to just click on the intro, right? This is all just a quick introduction. So you can see we've got a cannon here. You can do a variety of different things to change the settings. First thing you can do is click and drag it up and down. So you can change the height of the cannon that it's firing at in meters. On the bottom here, you can change the initial speed that it fires at. It's usually standardized at 15 meters per second. You can change the projectile. So right now it's set to pumpkin. This red button here fires the cannon. So there's my pumpkin that goes flying. But you can choose car, piano, a human. So whatever you want to work with, it doesn't make a difference to the trajectory. There's a target on the ground here that you can move back and forth, and that's something you're going to be sort of working with as you complete the little quiz worksheet that you'll be working on. If things look messy, you can always hit this eraser button here, or the reset button in the lower right corner will just bring it back to the initial settings. Final thing is in the upper left, there is 2 magnifying glasses. You can zoom out. You'll have to do that for one of the questions and zoom back in. But you're going to use this simulation for the last step here, step 6, to complete this Google or Canvas quiz, Intro to Projectile Motion PhET. If you click on that, it'll look like this, and the questions have instructions, and then a mix of multiple choice, fill in the blank, and the last one is sort of a more thoughtful question. So again, I will be here listening if you need help or if you're not sure how to operate the PhET simulation, but otherwise I'll give us 10 minutes to work on this, and then we'll come back together to review.
I have a question, Mr. Hank.
Yeah.
So, if we haven't finished Edpuzzle as in class, do we have to finish it as homework?
Yes, yeah, it'll be an assignment, so you can just have it paused and complete it later. Oh, well, no, sorry, the 30-second, that 30-second Edpuzzle?
Yeah.
No, don't worry, yeah, don't worry about that. No, that's not homework. No, that was just kind of a quick, silly thing. Ronan?
So we have the simulation open.
You can continue that as homework. I'm hoping using that PhET simulation was straightforward. How many of you were able to figure out how to hit the target 105 meters away? Everyone get it? Pretty much have to maximize everything, right? So what's the trick? What do you got to do to the height?
You have to change it to 15 meters.
High as it'll go? What was the angle that worked the best?
45.
45.
Yeah, about 45, sometimes 52, but 45 will definitely be the key one. So kind of interesting to think about. And this is, they use a cannon, but this is the kind of thing that if you've ever been to a circus where they've done these sorts of things, you do have to do a lot of math on that. Unfortunately, I mean, it's not a good example, but in warfare, mortar fire and things like that, or fire from naval ships, all happened in parabolas. So it's just doing a lot of math based on what angle and where's it going to land. But obviously drag and wind bring in other factors, which we will discuss in our next lesson. The only other thing I want to touch on was the last question, which I find kind of fascinating about us as humans. More than most other animals, we are very good at throwing things and hitting a specific target. Look at the sports we play, right? If you look at baseball, basketball, lacrosse, everything is about hitting a target. We are very, very good at making those calculations and throwing projectiles. So from an evolutionary standpoint, anyone have any ideas why? What was the evolutionary advantage of that? Because I don't think our ancestors were pitching baseballs at each other, were they? Anyone want to take a guess? Go ahead, Danielle.
I just said that maybe it's because first humans had to learn how to throw rocks to use as weapons or something. I don't know.
Yeah, no, that's exactly very good thinking, right? So again, if you think about Homo erectus and we started to walk upright, we started to use tools. And in my opinion, as you said, throwing rocks, this was the big step towards modern Homo sapiens in tool use, that we started to get good at throwing projectiles, spears, rocks. So what did that allow us to do more than our other relatives? or are rocks good at useful for? Ronan, you got an idea?
Wait, so I'm confused. What's the question?
So, what's the advantage of throwing projectiles, right? Especially if you think about our ancestors. What it relates to, just for the sake of time, is hunting, right? We got really good at throwing spears and killing things. A lot of times, too, just harassing animals, right? You could force them to run off a cliff or something like that. Made food acquisition much easier. If you think about it, too, acquiring fruit, rather than having to climb all the way up a tree now to get a fruit, you can throw stones and throw projectiles to get them down. This was kind of the big advantage and has stuck with us ever since. If you think about our evolution of our arms and again, look at what we're capable of now in terms of throwing, I think it's still kind of interesting. So anyway, we'll discuss more of that when we come back together and review the homework. Homework is to make sure you've wrapped up the 2 things we did in class. So make sure you've posted the Flipgrid and make sure that you have completed this quiz about the PhET. Otherwise, you're going to continue reading in chapter 5, 5.9 through 5.11, I think, where you're going to introduce drag, and we're going to start getting at the idea of orbit and the usual notes and reading reflection to complete. Questions on that? And I just want to emphasize there's no school on Friday. The reason for that is because midterm grades are being calculated and comments are being written. And so this is a good time now in all of your classes, but this one too, to check the grades tab. Reach out to me if you've got any missing assignments or if you need anything. I'm a little behind on my emails, but I will do my best to get caught up. So anyway, that's it for me, kids. Thank you very much. Have a good day.
Thank you.
Thank you.